All right, let's dive into one of the most fundamental, powerful, and honestly kind of weird forces in the entire universe, electric charge. It's happening around us right now, all the time, from a tiny little spark to a massive, epic lightning storm. It all kicks off with a mystery you've probably experienced yourself. You know the feeling, right? You slide across the car seat, you reach for the handle, and zap, you get that little shock. What in the world is going on there? It feels like some kind of strange magic, but I promise you, it is pure physics.
And what's wild is that little car door zap has some pretty impressive relatives. It's the exact same thing that makes your sweater crackle and spark in the dark. It's why you get a jolt from a metal pole on the bus. And on a much, much bigger scale, it's what creates the unbelievable power of a lightning strike. These are all clues in a much bigger investigation.
So, to solve this mystery, first we gotta identify our culprits. And it turns out, after centuries of people looking into this, there are only two suspects behind all of these electrical shenanigans.
This whole story actually started thousands of years ago. Early observers noticed something strange. If you rubbed a piece of amber with some wool, it suddenly got this new power. It could pick up light things, like feathers. That was the very first clue that there's this hidden force you could just wake up by rubbing things together.
And once scientists started really experimenting with this, they stumbled onto the absolute #1 rule of the game. They found this super simple pattern. If you charged up two glass rods, they'd actually push each other apart. But if you took a charged glass rod and brought it near a charged plastic rod, they'd pull right toward each other. And just like that, they discovered a fundamental law. Like charges repel, and unlike charges attract. Simple as that.
Now, you can thank the American scientist and founding father Benjamin Franklin for the names we use today. He was the one who suggested we call one type of charge positive and the other negative. And you know what? That convention has stuck around ever since. So, using Franklin's convention, here's how it works. When you rub a glass rod with a piece of silk, the glass becomes positive and the silk becomes negative. Do the same with a plastic rod and some fur, and the plastic becomes negative while the fur turns positive. See the pattern? It's always a pair. One object loses something to become positive, and the other one gains that exact same thing to become negative.
But you know, just knowing we've got positives and negatives isn't really enough. We need to find the motive. Why does this happen? What is actually being passed between these objects when we rub them together? To find that answer, we've got to go deep, deep inside the atom.
And here's the really mind-blowing part. The world around us isn't empty of charge at all. It is absolutely jam-packed with it. But in almost everything you see, the amount of positive charge from the protons inside an atom is perfectly, and I mean perfectly, balanced out by the negative charge from the electrons orbiting around them. The result? No net charge. Everything is just electrically neutral.
So when you rub that glass rod with the silk, you're not creating charge out of thin air. You're just knocking things out of balance. That friction gives some of the electrons on the glass atoms just enough of a kick to literally jump ship over to the silk. Now the rod is missing some negative electrons, leaving it with a net positive charge. And the silk, well, it's got a bunch of extra electrons, making it negatively charged.
And this reveals one of the most fundamental, unbreakable laws in the entire universe, the conservation of charge. The total amount of electric charge in any closed system never, ever changes. You can move it around, you can separate the positives from the negatives, but you can't make it and you can't destroy it. It's always accounted for.
Okay, so we know what charge is, we know where it comes from, and we know you can't get rid of it. But how do we actually describe the forces it creates? You know, how strong are they? It's time to open up the official rule book.
First up, a really strange rule. See, charge isn't continuous, like water flowing from a tap. It's quantized. That's a fancy word that means it only comes in tiny individual packets. Think of it like money. You can have $1 or a cent, but you can't have half a cent. The smallest possible packet of charge is the charge of a single electron. We call it E. You can have 1 E or 2 or a billion, but you can never ever have half an E of charge.
And just how much charge is in one of these packets? It is staggeringly, unbelievably tiny. The standard unit we use for charge is the coulomb. To put that in perspective for you, if you could somehow manage to move 1 billion electrons off of your body every single second, it would still take you almost 200 years to transfer just 1 single coulomb of charge.
So, how do we calculate the force between charges? Well, back in the 18th century, a physicist named Charles Augustin de Coulomb figured it out, and his law is just beautiful. It says more charge means more force. Makes sense. But here's the real kicker: distance. The force gets weaker really, really fast as you pull things apart. If you double the distance, you don't cut the force in half. You cut it down to a quarter of what it was.
And just how strong is this force? I mean, really? Let's compare it to gravity, which we all think of as being pretty powerful, right? Well, the electric force between one single proton and one single electron is about 10 to the 39th power times stronger than their gravity. That is a 1 with 39 zeros after it. It's not just stronger. For all practical purposes, it is infinitely stronger.
So this brings up a huge, mind-bending question. If this force is so unbelievably powerful, how does it actually work? How does it reach across totally empty space to push or pull on another charge?
I mean, seriously, think about it. This was a giant puzzle for physicists. They called it action at a distance. It's not like these tiny particles have little arms to reach out and grab each other. So what's the messenger? What's carrying the force from one place to another? The answer is one of the most elegant and beautiful ideas in all of physics: the electric field. Here's the concept. A charge doesn't actually act directly on another charge. Instead, it changes the very fabric of the space all around it. It creates this invisible field of influence. Then, when another charge wanders into that field, it's the field itself, right at that spot, that does the pushing or pulling. The field is the middleman. And this field isn't just there, it has both a strength and a direction in every single point in space. And by convention, scientists decided to define the direction of the field as the way a tiny imaginary positive test charge would get pushed if you dropped it right there. So you can picture it like this. A positive source charge is like a tiny sun. The electric field lines radiate straight out away from it in every direction. A positive charge placed nearby would get pushed away. But for a negative source charge, it's the exact opposite. It's like a cosmic drain, with all the field lines pointing directly inward, toward the center. A positive charge would get sucked right in. Which brings us back around to the biggest, most mind-bending question of all. We have just established that this electric force is trillions upon trillions of times stronger than gravity. So, why isn't our world constantly and violently flying apart or catastrophically crushing itself into a single point? The answer goes all the way back to that idea of perfect balance. And it's the key to understanding how these incredible forces build the stable, solid world that we see every single day.